Our next talk, Eagle, is about sketch deployment. Our presenter, Xiang Chen, is a second-year PhD student from Zhejiang University in China. Before that, he received his master's and bachelor's degree from Fuzhou University. His current research interests include programmable networks and network management. Okay, please take your floor.
Thanks for the introduction. Okay, hello everybody. Good morning. This is Xiang from Zhejiang University. Today, I'm going to present our work, Eagle, towards scalable and near-optimal network-wide sketch deployment in network measurement. And this is a joint work by Zhejiang University, Southeast University, Peking University, Yangzhou University, and ZTE Corporation. Network is the basic of key infrastructures, productions, and ISPs. However, the exploding scale of network applications and the users has brought a lot of challenges to the security and the management of networks. In response, to discover network status and serve management, network-wide traffic measurement is widely applied as a fundamental methodology for understanding the dynamics of networks. It provides the key information for diverse network management needs, such as anomaly detection, failure recovery, and performance evaluation. Although the measurement statistics are useful, explosive growth in network user number and traffic scale has led to severe degradation of measurement performance. Specifically, previous network measurement techniques, such as traffic sampling and mirroring, suffer from both low accuracy, high memory overheads, and high computation resource consumption. Therefore, how to perform network measurements accurately in real time under resource constraints has become an important problem. To address such problems, recent advances leverage sketches to achieve high accuracy and low resource overheads in traffic measurement. A sketch assembles counter arrays, hashing functions, and updating functions. For each packet, sketches on programmable switches first invoke hashing functions to locate the counter and determine to increase or decrease counters with values. When traffic arrives, they measure various flow statistics, such as heavy hitters and super spreaders, at run rate. In general, existing solutions choose to deploy multiple concurrent sketches and collaborate them to collect various statistics. Since a single switch exhibits strict resource limitations, such deployment is realized in a network-wide setting. In particular, users expect network-wide sketch deployment to be optimal and scalable simultaneously. By optimality, sketch deployment needs to minimize switch resource consumption and its impact on end-to-end performance. And by scalability, sketch deployment needs to make timely decisions about where to place which sketches. That is, reducing deployment time as the number of switches and the sketches increase. However, sketch deployment is non-trivial due to three requirements. First, users often choose multiple sketches because different sketches are used in different network environments and for different measurement objectives. Second, sketch deployment needs to satisfy various constraints. Switch resources are scarce. Making the best use of switch resources helps avoid deployment failures and deploy more sketches. Also, there are various network-wide constraints, such as link bandwidth, latency, and throughput. Third, we need to achieve efficient deployment and update sketches based on network changes. Reacting to frequent network dynamics, such as topology or security intent changes, needs timeliness. For example, when topology changes occur, sketch deployment should quickly place sketches on new ingress switches to cover high-speed traffic. Otherwise, stale sketch deployment remains in use, dropping measurement accuracy. To satisfy these requirements, existing solutions use MIP or heuristics. However, they trade scalability for optimality in network-wide sketch deployment, or vice versa. Specifically, most existing frameworks for network-wide sketch deployment preserve resource limitations. They formulate network-wide sketch deployment as an MIP problem with switch resource limitations as constraints, and they depend on off-the-shelf MIP solvers such as CP-Lex and Groby to solve problems. Unfortunately, it is NP hard. Consider a case where 50 sketches are deployed on a network with 100 switches and 300 links. This case translates to the MIP problem with at least 1.6 million variables. MIP solvers consume several hours for problem solving. In practice, the deployment time grows as the number of sketches and the network scale increase, as shown in Figure 2 and Figure 3. As a result, the limited scalability of MIP solvers is the primary issue of existing sketch deployment frameworks. Another approach refers to heuristics. However, even for highly skilled experts, they still require non-trivial efforts to design a near-ideal heuristics that achieves a reasonable balance between the optimality and the deployment time. Even worse, heuristics are hard to maintain as the scale and the input change, often do not extend to modified objectives, and are suboptimal. Also, as shown in Figure 1, treating optimality means consuming more switch resources. Therefore, heuristics not only require laborious human efforts, but are also time-consuming and suboptimal. In this paper, we propose EAGLE, an efficient network-wide sketch deployment framework. Our design goals are threefold. First, we aim to support diverse deployment objectives. Second, we meet heterogeneous constraints in programmable switches and networks. And finally, we achieve real-time updating of sketches based on network changes. In response, EAGLE assembles 4 optimization techniques, including problem decomposition, stateful sketch deployment, parallel sketch deployment, and topology simplification. Before problem decomposition, EAGLE abstracts the substrate network into one big switch, or OBS. There are different types of switches in the network. To reduce the complexity faced by network administrators due to heterogeneity, EAGLE abstracts the substrate network into a single OBS to hide heterogeneity and substrate details. Then, to achieve high scalability, EAGLE breaks the monolithic problem into smaller subproblems. And this reduces the search space while enabling us to pick the techniques that best suit each subproblem to speed up problem solving. In particular, problem properties can be categorized into 2 classes. First, the intra-switch class contains the properties for the deployment of sketch components on switch stages. It includes the objective of minimizing the number of occupied stages, the decision variables of deploying sketch components on stages, and the intra-switch constraints. Second, the inter-switch class has the properties of selecting enough switches to run sketches. It includes the objective of maximizing end-to-end performance, the decision variables that select switches that deploy sketches, and the inter-switch constraints. Since the deployment of sketch components on switch stages doesn't affect the selection of switches, the 2 classes are interdependent. Such loose coupling enables us to safely decompose the original problem into P1 and P2. When solving P1, we observe that sketch components exhibit 3 types of similarities. The first is sketch-level similarities. Administrators need to deploy several concurrent sketch instances to meet multi-tenant requirements. Many of these instances are identical in structure and functionality. The second is matrix-level similarities. For multiple metric sketches, they use identical metrics to measure traffic. And the third is array-level similarities. For a single matrix, its counter arrays share the same number of fixed-width counters. And motivated by the above observation, we designed stateful sketch deployment. Our key idea is to identify all the identical sketch components and only deploy one of these components on the OBS. Then Eagle reuses its results for the remaining components. So it reduces the number of redundant deployment processes while still obtaining complete deployment decisions. As a result, in Figure 2, Eagle significantly reduces deployment time compared to existing solutions. In addition to stateful deployment, we find that the process of deploying sketch components on OBS stages can be decomposed into several concurrent tasks. The reason is that interdependent sketch components must be deployed on different stages, so their deployment processes do not interfere with each other. As a result, the tasks that deploy different types of interdependent components on OBS stages are interdependent, making it possible to perform them in parallel. So Eagle exploits parallelism. It classifies sketch components into several classes, each of which only contains a specific type of interdependent sketch components. And then we can split the entire process that deploys sketch components on OBS stages into several concurrent tasks. Each task deploys a specific class of sketch components on a few OBS stages. And all tasks work in parallel, shortening deployment time. Therefore, Eagle reduces deployment time by a significant amount compared to existing solutions. Then we solve P2. The substrate network contains both programmable switches and non-programmable switches, while only programmable switches are considered useful for sketch deployment. So Eagle simplifies the network by transforming it into a programmable one, where all switches are programmable. Doing so reduces the network scale and the deployment time. Figure 1 shows an example. The network has 2 programmable switches, while others are non-programmable. Eagle executes 3 steps. First, it embeds switch 2 onto the red links in Figure B. It obtains 3 loop-free new links from E7 to E9. And then it acquires 5 links from E10 to E14 by embedding switch 3 onto the red link in Figure C. Since the link E10 visits switch 2 twice, it contains a loop, so Eagle removes this link. And third, Eagle removes the last non-programmable switch, switch 4, from the topology and returns the simplified one in Figure D. Such simplification doesn't alter the original topology information, such that it has no impact on the optimality of solving P2. To evaluate Eagle, we pick 2 sets of topologies that vary in structures on scales. For structures, we select 5 wide array topologies from the Internet Zoo. We set all switches to be programmable. And for scales, we choose the fetch tree data center topology and vary its number of ports to obtain 5 variants. We randomly choose 30% of switches to be programmable with respect to real-world statistics. For sketches, we implement 20 sketches in P4. Unless specified elsewhere, we set the number of counter arrays per sketch to 10. And for each array, we set its memory to the maximum capacity of a single stage. We configure other sketch level parameters based on their original papers. We have implemented Eagle on Groby. Eagle accepts the sketches, each of which is defined in a P4 program. It identifies sketch components from each program with the help of off-the-shelf P4 compilers, and it uses the branch and bond algorithm offered by Groby to solve its subproblems. We compare Eagle with existing frameworks. In addition, we implement greedy-based heuristics using greedy and BFS to solve deployment problems. We first quantify the overall timeliness of Eagle. We use Eagle and the comparison frameworks to deploy the 20 sketches on each of the 2 sets of topologies, respectively. In Figure 1, Eagle reduces the deployment time by up to 189 times, and then we fix the topology to Internet 2. Figure 2 shows that Eagle reduces the deployment time by up to 255 times. We then evaluate the timeliness of Eagle's components. In Figure 1, the problem decomposition improves the deployment speed by up to 0.4 times, and Figure 2 indicates that the stateful sketch deployment reduces the time by up to 8 times. Also, in Figure 3, the parallel deployment reduces the deployment time by up to 5 times, and in Figure 4, the topology simplification significantly reduces deployment time. For example, in C5, it reduced the time by 3 times. Finally, we evaluate Eagle's optimality. We use Scalable to directly solve the deployment and record its results. Then we compute the divergence between Eagle with optimal. Figure 1 and Figure 2 show that the optimality gap of Eagle is near 0, which means that Eagle preserves near optimality. Instead, Greedy is suboptimal. It consumes more switch resources and incurs higher latency than Eagle. In conclusion, network-wide sketch deployment is crucial for network measurement, while existing solutions suffer from excessively long deployment time. And in this paper, we propose Eagle for efficient network-wide sketch deployment. Eagle exploits the OBS to decompose sketch deployment into subproblems. And it solves the subproblems in parallel and incorporates optimizations into its problem solving. And our results show that compared to existing frameworks, Eagle reduces the time by up to 255 times while retaining near optimality. That's all of my presentation. Thank you.
Okay, let's take questions.
Qiao Xiang from Xiamen University, China. Yeah, thanks for the talk. Very interesting. I actually have 2 questions. So in the stateful deployment, you mentioned that my understanding is that you basically try to reuse, if there are 2 sketches doing the same job, you just deploy one, basically to reuse them to avoid wasting resources. But wouldn't that cause any security issues? For example, maybe we have 2 sketches need to be deployed from different tenants or different applications, but essentially, because the data actually would be on sort of like different private network, and maybe would contaminate the result and so on. Have you thought about that, or this is not an issue in your setting?
Mm-hmm. Thank you for such a great question. And in the current form of Eagle, we didn't consider security considerations, but I think we can maybe develop some secured techniques into Eagle in the near future. Mm-hmm.
Yeah. The second question is that in your motivation part, you mentioned that you want a solution that can react to network dynamics, mm-hmm. and but in the later technical part, I might have missed that. Mm-hmm. Could you elaborate on how do you address that in Eagle?
Thank you for your question. And we address network dynamics in twofold. First, we will place new sketches on ideal switches that are not used in previous deployments. And second, if we wish to deploy sketches in an optimal manner, we need to recompute the decisions at runtime, so we can use Eagle to accelerate this process to enable such timely decision. Mm-hmm.
All right, thank you so much.
Thank you.
Okay, let's thank our speaker again.